Hi, this video will cover section 8.2, operations with matrices. The objectives for this section are decide whether two matrices are equal, add and subtract matrices, and multiply matrices by scalars, by a constant. Also, multiply two matrices. And lastly, use matrix operations to model and solve real-life problems. So the first objective is to check how to check if two matrices are equal. Well, first, let's see what is a matrix. A matrix, it is a rectangular array of numbers. So rectangles also include squares. So for example, the two matrices that you see here, they are square matrices because the dimensions are two rows, horizontal, horizontally, we refer to them as row, and the columns, so this is R1 for row 1, R2 for row 2. And for the columns, it has two columns as well. So this is column 1 and column 2. So we could say that this is a matrix with two rows and two columns. So we refer to them as 2 by 2, like a multiplication. 2 by 2. And so those are the dimensions. The rows are horizontally and the columns are vertically. So going back to our definition, so a matrix can be denoted by a rectangular array of numbers such that, and here we have a subscript that looks like an 11, but in reality it is denoting first row, first column. So the term here will be A11, A12, A13, and that means first row, first column, first row, second column, first row, third column. And here the three dots, it indicates that we don't know how many terms are in between, but the last term of that row will be referred as first row and column. So in this matrix, we could say that the number of columns will be n. N is the number of columns. And the number of rows, if we look at the last row, you could see that we have M1. So that means that we have M rows. Since we start with first row, second row, third row, and then all the way to M. And for the columns, we have N columns. And so the last term here is going to be the term with in the row M and column N. So you can see here that we're using an uppercase letter to give the matrix a name. So we use uppercase letters to denote matrices. And the lowercase, it signifies that they are entries, or we call them elements inside the matrix, and so we just match the uppercase to the lowercase. Here the notation I and J, we use I to denote the number of rows and J to denote or generalize the number of columns. So those will just be numbers, but we use I and J to generalize them. In this case, we're using M for the biggest, for the last row, and N for the last column. So going back here to the representation of matrices, so we could use other uppercase letters, B or C or M or I. We will be using that. And a matrix can be denoted by a representative element, so that would be what we had here. and then the uppercase is to denote the matrix. And then we can have all the numbers there. Now, remember it says here rectangular array. So rectangles, as I told you, they also involve squares. So the way that we check if two matrices are equal is by checking that all of their entries are equal. But also, if we are told you have these two matrices, as you can see here, we have two matrices, and you can see that the number 2 is in the same position as the first row, first column. So what we're saying is that the first entry, first row, first column is equal to 2. So A sub 1, 1 is 2. Then because we have first row, second column matching the location, or we also call it the address of the matrix, first row, second column, we could say that A1, 2 is equal to -1. Also, we have second row, first column, right here, number -3 is second row, first column. So A sub 2, 1 is -3. And then we have second row, second column, matching here 0. And so we can say that A sub 2, 2 or A2, 2 is 0. And so that will be true for every single entry in the matrix. To generalize that, we're using here, we have two matrices. Let's say they're called A, the other one is called B. So all the entries inside matrix A are denoted with the subscript I and J, and all the entries in matrix B are denoted with the subscript I and J. So if we say that those two are equal, is because for every single entry in matrix A, is going to be equal to every single entry in matrix B. And that is true for all I. I is the number of rows. So for the rows, we use they start on row 1 and they end with row M, like we say here, M rows. So for rows 1 to M. And then for columns, that will be J, also from 1 to J. 1 all the way to, to N. Remember, N was the last column. So that is true for every single entry. So every corresponding entry, it will be equal if we say that the two matrices are equal. So what we're going to do next is go over addition and scalar multiplication. So first we will do addition. The first condition here is going to be that the dimensions of each matrix match perfectly. That's the only way you can add them. So the dimension here, your textbook is using the word order. So if we say matrix A, it has m rows and columns, then their sum in, both of them, A and B, have the same order or same dimensions. So then their sum is the same dimensions, m by n matrix, given by, and here we're representing that we're going to add all the elements of matrix A plus all the elements of matrix B, and they have to have the exact same location within the matrix. So same row, same matrix. Same row, same column. So here, we are going to have to add -1 plus 1 because they are located in the first row, first column. So you can see that here. And then we will be adding 2 plus 3, so you could see that here, 2 plus 3, because they're both in the first row, second column. And then we have 0 plus negative 1, which you can see here because they're both in the second row, first column. And then finally we have 1 plus 2 because they are in the second row, second column. And what happens when they don't have the same number of rows and same number of columns, or if they are of different order? Well, we simply say that they will be undefined. So the sum of matrices of different orders is undefined. So you have to make sure that you have the exact same number of rows, exact same number of columns. So let's just finish this problem. We have here negative 1 plus 1 is 0. Then we have 2 plus 3 is 5. And then 0 plus negative 1 is negative 1. 1 plus 2 is 3. And that's it. That is our answer for the sum or the addition of those two matrices. So the next one, again, we see the same dimensions. This one is a 2 row by 3 column. And the one on the right side is also 2 rows, 3 columns. So they are both of 2 by 3. So if we add the two matrices that are 2 by 3, the resultant matrix will also be a 2 by 3. And this is pretty easy because if you notice, we're going to be adding a 0. And in fact, a matrix that has zeros everywhere is called a zero matrix. So 0 plus 0, 0. And then 1 plus 0, 1. Negative 2 plus 0, negative 2. 1 plus 0, 1. 2 plus 0, 2. 3 plus 0, 3. And I'm missing this one here. Okay, next we're going to have this type of matrices are also known as vectors because their dimensions are 3 rows and 1 column. Or we could also call it a column matrix. And this one is the same. So remember, they have to have the exact same dimensions so that we can add the corresponding entries. So 1 plus negative 1 is going to be 0. Negative 3 plus 3 is 0. And then negative 2 plus 2 is 0. And in fact, this one has the name. It's called the zero vector. Okay, now the next question is the sum of A plus matrix A plus matrix B. And so just so you know the dimensions of matrix A, it has 3 rows and it has 3 columns. So this is a 3 by 3 matrix. And if we look at matrix B, we have 3 rows and 2 columns. So because the dimensions are not the same, we are just simply going to say that A plus B is undefined, or it doesn't exist, or maybe web assign has that option, the DNE for does not exist. Okay, so as you can see, addition is pretty simple. And actually, we didn't have any example with subtraction, so I'm going to give you one. And what we do is just very similar to what we do with real numbers. So let's say we have 2, negative 3, 4, 0. And then here we're going to have minus, I don't know, 1, negative 5, negative 2, and 3. Something like that. Okay, so I'm gonna write one step here. So 2 minus 1. So it's gonna be 2 minus 1. Then negative 3 minus negative 2. Negative 3 minus negative 2. And then 4 minus negative 5. 4 minus negative 5. And then we have 0 minus 3. 0 minus 3. And I do like to do this because, as you notice, we have several double negatives. And so I want to make sure that I don't overlook any of those because I am subtracting, and so that's going to create a double negative situation. So let's start with our first row, first column. So 2 minus 1 is 1. Then we have here 3 minus minus, that makes a positive. So this is in reality negative 3 plus 2. And then we have here for the second row, first column, 4 plus 5 because of the double negative. And then we have 0 minus 3, which is negative 3. And just to finish, we have a 1, and then here negative 3 plus 2 is negative 1. 4 plus 5 is 9, and then we have here negative 3. So the next objective is matrix addition and scalar multiplication. Well, scalar multiplication, but then we will be combining it with addition. So we have that in operations with matrices. Numbers are usually referred to as scalars. So they're just going to be constants. They could be positive, they could be negative, they could be a fraction, they could be an integer. And they could also be 0, but most of the time we use scalars other than 0, but they could still be 0. And if we multiply a matrix times the scalar 0, we will get the 0 matrix. So they are real numbers. And we could always multiply a matrix. Remember, we use uppercase letters to denote a matrix. And the lowercase letter here, C, is denoting a real number. So if we do that, what we are going to have is, we have here matrix A, and the order is m by n. That means m number of rows, n number of columns. And if we multiply that by C, which is a scalar, then the product, the scalar multiple of A multiplied by that particular scalar C, that's what we're calling it, it's going to be the product of C times every single entry inside matrix A. So it's kind of like distributing a number in that is outside parentheses, and then you have some expression. You have to distribute it to every single entry that you have there. So for example, let's make a matrix. Let's say that C is equal to 2, and then we have matrix A is going to be equal to, I'm just going to 1, 2, 3, 4. So if I want to multiply 2 times A, I'm going to have to distribute that 2 to every single entry inside the matrix A. And so to do that, we treat it just like if it was parentheses, and we distribute that scalar to every single number inside the matrix. So in this case, we will have 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and 2 times 4 is 8. And that will be the result. So it is often convenient to rewrite the scalar multiple C times A by factoring C out of every entry in the matrix. So for example, here we have a matrix with fractions. As you can see there, all the numerators are being divided by 2. So 1/2, negative 3/2, and so on. So if we factor 1/2 out of every single entry, it's like if you had 1/2, like right here, 1/2, and then you divide that by 1/2 because we're factoring 1/2 out of it, as you could see here. And you could see here. So if we do that, we will get a 1. And so that's why we have a 1 right here. Now, if we have negative 3 halves, and we are going to factor out 1 half, the 2's here will cancel, and we have negative 3 over 1. So that's why we have negative 3. And here we have 5 halves. So if we factor out 1 half, it's like we're dividing by 1 half. If you just want to verify, we can have 5 times 2 by multiplying the outer entries, and then the inner numbers will be 2 times 1. The 2's cancel, just like I did over here, and we have 5 over 1, which is 5. And then finally, we have here 1 half. If we factor 1 half out, we get a 1, just like on the first row, first column. So then what we could do is rewrite it so that the scalar is just factor out of the matrix, like you can see here. And then you have the entries inside the matrix. Now they're all integers. So sometimes that is convenient. Next thing we have here is that if you have a negative in front of a matrix, of the name of the matrix, it represents the negation of A, or the opposite of A. So that opposite would mean that for every entry in A, the entry in negative A will have the opposite sign of each entry inside A. So meaning that we just multiply negative 1 times A, and based on the scalar multiplication definition, you have to distribute that negative 1 to every single entry inside matrix A. So moreover, if A and B are of the same order, then A minus B will be the same as A plus negative B. And that is why we don't really say we're going to learn matrix addition and subtraction, because in reality, addition and subtraction are the same thing. Subtraction is just addition, but with negative numbers. And so if we're saying A minus B is the same as A added to the opposite of B, which is the same as A plus negative 1 times B. So that is how we define subtraction, just addition of the opposite of B. And remember, if it has a negative in front of it, it's because every entry is being multiplied by negative 1. Now, let's go over some of the properties of matrix addition and scalar multiplication. So we have that the properties of matrix addition and scalar multiplication are similar to those of addition and multiplication of real numbers, except for one, but actually we're not going to discuss that one yet. So right here, yes, for addition, just like we have with numbers, commutative property of addition, like 2 plus 3 is equal, oops, that's not equal. Okay, so 2 plus 3 is equal to 3 plus 2. That is the commutative property with real numbers. So the same thing applies to addition with matrices. Then we have the associative property of matrix addition. And so here you could see how we have B and C grouped together, and then here's A and C grouped together. And then you add on the left side, we're showing that B and C get added together first, and then you add A. And then on the right side, we're showing that you can add A and B together and then C. That property with numbers will be something like 2 plus, and then we have here 4 plus, I don't know, 1. And so that is the same as adding 2 plus 4 first and then adding 1 at the end. So 4 plus 1 is 5, plus 2, that will give me 7. And here 2 plus 6 is, 2 plus 4 is 6, plus 1 is also 7. So that is the associative property of matrix addition. Now we have the associative property with of scalar multiplication. So here imagine you have two different scalars. One is C and the other one is D. Remember, scalars are numbers, real numbers. And here the only matrix is A. So what we could do is, let's think that we have like 4 times 3 and then times matrix A. So one thing we could do is multiply 4 times 3, and that will give us 12. And then that 12, we can then distribute it to matrix A. Or we could do it like it says here. We could multiply first, leave our 4 out, and then multiply 3, the scalar 3 times matrix A. And then after we do that, we distribute it to, we distribute the 4, so it would still be the same, 12 times A. So that is the associative property of scalar multiplication. Then the next one is the scalar identity. And so every set of numbers, or in this case matrices, they have an identity, and that would be the number 1 for scalar identity, meaning that if you multiply a 1 times every single entry inside matrix A, you will get the exact same entries for all of them, because it's just like with real numbers. If you multiply 1 times 5, you still get 5. So 1 is the identity for real numbers, for multiplication. Multiplicative identity, that's the correct name. And so is number 1, so is that for scalar identity. So for scalar identity is in multiplicative identity for real numbers, same thing. 1 is the identity. Then we have the distributive property. So for this one, what we're distributing is the constant. So we could distribute the constant to A and then to B, like you have here. And then we can add the two matrices. Or we could first add the two matrices and then distribute the constant after. So either way, they are equal, and that is the distributive property. Then we have number 6 here. Now we have two scalars, and what we could do is add the two scalars first, like you could see here, and then distribute that to matrix A after we add the scalars. Or we could distribute the first scalar to A, the second scalar to A, and then we add them. So that is another distributive property. But number 5 is showing two matrices, number 6 is showing two scalars. But as you could see, we could distribute, and left side is equal to the right side. So next concept is for the property of addition of real numbers, is that the number 0 is the additive identity. So 0 is the additive identity, and then here I did tell you that 1 is the multiplicative. So please write this down, because we're going to need this concept when we get to section 8.1. And I know I changed the order. I want you to watch 8.2 first. There's a reason for that. Well, several reasons. Once you see the video from 8.1, you'll see why. So we have two types of identities. One is the multiplicative identity, meaning that if you multiply a matrix times 1, you get the same matrix. And then 0 is the additive identity, meaning that if you add 0 to every entry in the matrix, you still get the same entries. So if you have matrix A with the order of m by n, or dimensions, m rows, n columns, and then 0 is the 0 matrix as the one that we saw previously. And so if we add those two matrices, A plus the 0 matrix, we will get the exact same matrix that we started with. And that's why we refer to that as the additive identity. So 0 will be the additive identity as a scalar, but the 0 matrix will be the additive identity for the matrix, for the set of all matrices that match the same dimensions. So for example, we have two different ones here, two different examples of the 0 matrix. The first one is a 2-row by 3 columns. Remember, the first digit indicates the rows and the second digit indicates the columns. And then here we have a 2 by 2, so 2 rows and 2 columns. Okay, so now let's move on to matrix addition and scalar multiplication. So as I mentioned earlier, the algebra of real numbers and the algebra of matrices have many similarities. For example, we can compare the following solutions. So the example on the left side of your screen, it contains an example of solving a typical equation. We see lowercase variables here, unknown variables. And then here on the right side, we have matrices. So that's why we have uppercase letters. So let's go over the example on the left first. And we have how x plus a is equal to b, and we need to solve for x here. As you can see here, solve for x. So we see the plus a, and you know that I tell you always to just like take it across, right? And it will do the inverse operation, as you can see here, minus a. So the correct way to do this, is to just write it on both sides. So this will be equivalent to saying like I'm gonna subtract a from both sides. So minus a, and that will cancel here, and then you have b minus a on the right side. So the correct way is to add or subtract, but on the same row, not below, like it is here. So if we do that, you could see that if you put plus a minus a is equal to 0. So that's why we're able to say they cancel. And then on the right side, if you have b plus negative a is the same as b minus a, as you can see there. So then what is x plus 0? That will just be x, because 0 is the additive identity. And then the result is b minus a. So we will use the same idea with matrices, and here we are going to solve for matrix X. Sometimes that matrix might be made out of unknown variables. So for example, if we have matrix X plus matrix A is equal to matrix B. So what we want to do is isolate matrix X. We want to leave it by itself. So what we need to do is add the opposite of matrix A, which is negative A. So those two are opposites. And we do that because when we add those two together, we are going to get the zero matrix. So then, since we're adding that negative A matrix to matrix A, we have to do that to the other side. So we add negative A on the right side. So on the left side, we already said they will cancel because these two are opposites. So they give us the zero matrix. And then on the right side, we have matrix B plus negative A. So it's the same as B minus A, as you can see there. So that will be the solution. And here, X plus 0 will just be X, like that. And so we're going to use that same idea to solve some of the problems that are in the homework. So we're going to move on to matrix multiplication. And what we have here is the way that we have it defined. And if we have two matrices A and B, and here matrix A is of the order m times n, m number of rows, n number of columns. And then we have matrix B, which is n by p. So we're going to find the product of multiplying A times B. And A times B is going to be the product where we take every entry of every row of matrix A, and we multiply it by every single column of matrix B. And so our resultant matrix will actually have the dimensions m by p, the number of rows of the first matrix times the number of columns of the second matrix. And so those entries are actually listed here. So you start with the entry of first row, first column, and then you multiply it by the entries of B. So it makes more sense when we do an example. So, but the first thing you have to learn is that if we have matrix A, which is a matrix of m by n, and we're multiplying it by matrix B, that is an n by p. So we have to make sure that the two numbers here, n and n, that they match. They have to be equal. So if they are not equal, then the matrix product is undefined. And I'm going to highlight what we're saying here. So we have to check that the number, remember this is for columns of matrix A, matches the number of rows of matrix B. And what we are going to be multiplying will be the rows of matrix A, which is here, times the columns of matrix P, and those will be the dimensions of the resultant matrix. So we are gonna, here we have it in terms of ith, like first, second, third, fourth, fifth, sixth, and j. So it says the entries from the ith row of A by the corresponding entries of the J column of B. So the columns, the rows from A, the columns from B. Okay, so we're going to see how this is done. Oh, and by the way, if those two numbers in the middle do not match, then simply the product is undefined. And I want to just show you quickly that if I was to reverse this and try to find B times A, matrix B, it has N. Well, I'm going to make more space. So matrix B is N by P, and matrix A is M by N. So if that was the question, and remember we have to check that those two numbers in the middle match. So if we reverse the order of the matrices, you can see how the numbers in the middle do not match. They're different. So then we say that BA is undefined. So as you can see, matrix multiplication is not commutative, and I'm sure it is mentioned somewhere. I don't see it, so let's just write it down. Matrix multiplication is not commutative. And there are some special cases where it is, but most of them it's not. So just one simple counterexample makes it not be true for all. So let's get back, and here's just maybe not a very good example. So I prefer to do one with numbers. And it says here to find the product of matrix A times matrix B. So we have matrix A. Let's check the dimensions first. We have 3 rows. Remember, the row has the number of rows must be mentioned first. And we have 2 columns. Matrix B, we have 2 rows and 2 columns. And so we have to make sure that the number of columns in matrix A matches the number of rows in matrix B. And so those are equal. So our product is, we're going to be able to compute it. And the resultant matrix, our answer, is going to be of order 3 by 2. So 3 rows, 2 columns, because those are the numbers that are on the outside. Okay, so we mentioned that we were going to be taking the rows from matrix A and then multiplying them by the columns of matrix B, like you could see here. And so that is why we have to have this number in the middle matching, so that we have 2 entries here, 1, 2, because we have 2 columns, and we have 2 entries here, 1, 2, because we have 2 rows. So let's get started, and what we're going to do is the following. I want you, since we know the resulting product will be a 3 by 2, I want you to draw a rectangle that will have, oops, that's totally wrong. So we're going to have 3 rows and 2 columns. Oh, again. Okay, so 2 columns, 3 rows, right? 3 by 2, 3 rows, 2 columns. So for our first, our top left corner, we are going to take the numbers that I have highlighted. So we're going to take well, let's do this first. I would like for you to label each of those little rectangles, which I'm going to call them cells. So here we have the first row, first column, first row, second column, second row, first column, second row, second column, third row, first column, third row, second column. And what we're going to do now is take always the row will come from matrix A. So I'm going to highlight that. The row will come from matrix A. And the column will always come from matrix B. So this is kind of like matrix multiplication with training wheels, like when you learn how to ride a bike. Okay, so we are going to take now the numbers that are highlighted. So we're going to say -1 times -3, and then plus 3 times -4. And so let's just leave it like that, and then we'll do the multiplication next. Okay, so then we move on to the next space, and now we are going to take the first row times the second column, and this will be -1 times 2 and then 3 times 1 plus 3 times 1. Okay, let's move on now to the second row. So we take second row from here and first column from here. And so that will be 4 times -3 plus -2 times -4. Then we move on, and now we're going to take second row, second column. So it will be 4 times 2 plus -2 times 1. Okay, we move on now to the third row of matrix A, and we start with the first column of matrix B. So this will be 5 times -3 plus 0 times -4. Then we move on to third row, second column. So we're going to have 5 times 2 plus 0 times 1. And now we're going to carry out the product and the addition. So we have here that -1 times -3 is +3. -4 times 3 is -12. So if we combine that, 3 minus 12 is going to give me -3. Then we move on to the next side. First row, second column. So -1 times 2 is -2. 3 times 1 is 3. Negative 2 plus 3 is 1. So that goes here. And I might need a little more space here. Because remember, our solution will be 3 row by 2 column. Then we move on here to second row, first column. 4 times negative 3 is negative 12. Plus negative 2 times negative 4 is positive 8. And so negative 12 plus 8 will be negative 4. Then we have 4 times 2 is 8. Minus 2, and that equals to 6. And then last row, third row, first column, we have negative 15 plus 0. So that is negative 15. And then finally we have 10 plus 0. So that is 10. And so that is matrix multiplication. Now I want to show you quickly that if I was to ask you what is the product of B times A, that would be undefined because matrix B is a 2 by 2 and matrix A is a 3 by 2. So you could see how the numbers here in the middle, they are different. They're not equal. And so therefore BA is undefined. So once again, proving that matrix multiplication is not commutative. So we have some examples here, not examples, I'm sorry, a list of properties of matrix multiplication. So it is associative. You can multiply BC first and then A times BC. As long as you don't break any of the rules of the dimensions and all of that, or you can multiply A times B and then times C. Also, we have the distributive property, so we could, here we have multiplication and addition of matrices, so we could add matrices B and C first, and then we can multiply A times B plus C, or we can multiply A times B and then A times C and then add them at the end. And we should get the same thing as long as we do it correctly. Another distributive property is for, we have here addition and then multiplication. Or we could also do like what was above, distribute matrix C to A, like you see here, and then distribute matrix C to B. You do the two products and then you add them. And then finally here we have the associative property of scalar multiplication. So we have scalar C, and then we have AB. So we could distribute C to matrix A first and then do the multiplication, or we could distribute C to matrix B and then do the multiplication, and we should be able to get the same if you do it correctly, of course. Okay, so we have another new concept here. This is called the identity matrix. And identity matrices are square matrices, meaning that they have the same number of rows, same number of columns. And they also have ones in the main diagonal, as you can see here. That is the main diagonal that starts from the top left to the bottom right. And so everything else below and above the ones, they are going to be zeros. So you could see here, these are zeros. So every single entry. And you see a subscript here, n, because it is a matrix of n by n order, or the number of rows matches the number of columns, just like a square will do. So they must be square. Okay, so just like we have a multiplicative identity with numbers, for example, 3 times a number that will give you the same number is 1. So the number 1 is set to be the multiplicative identity for real numbers. So the identity matrix happens to be the identity matrix for all matrices. So we could see it here. And so if you multiply a matrix times the identity matrix, like we have it here, here we have matrix A, here we have matrix I, and this is a subscript 3 because it's a 3 by 3, 3 rows, 3 columns. So if we do that, we will be getting the exact same original matrix that we started with. Just like multiplying a number times 1 gives you the same number. Next, I have the example of identity matrix times matrix A, and we will also get the same matrix A. This is one of the few examples where multiplication is commutative. You can have the identity matrix on the left or the right, and you will still get the same as the product, which in this case is A. Okay, so applications. Matrix multiplication can be used to represent a system of linear equations. Note how the system below can be written as the matrix equation AX equals B. We call this, and we will go over this more in detail in section 8.3. We call this the coefficient matrix. Well, first, this is a system, as you can see here. The A sub 1, 1, A sub 1, 2, and all of that, those are numbers, real numbers. So this is a coefficient matrix, matrix A. And then matrix X is the one that contains your unknown variables. And the last one here is the matrix that contains your constant terms. Like the number after the equal sign that is not related to a variable, it's just a constant. So that is how you can break a system of equations into matrices. And from there, we should be able to solve a system. For us to solve that system, we will be using the concept of an inverse matrix. And the idea is it's actually pretty simple. What we do is we multiply the inverse matrix. We will discuss that more in 8.3. On both sides, as you can see here. And the idea is that here, if you multiply a matrix times its inverse, it's going to give you the identity matrix, like a 1. And then you get that times the variables. And so here, multiplying the inverse of A times B will give us the solution to the system. And remember that identity times any matrix, you get the same matrix. So that is the idea that we're going to be using in section 8.3. Let me just highlight a few things here. X is the, and B are column matrices. Remember, this was the constants, and then X was the unknown variables. Okay. So that is one of the applications. Now, a way to solve systems that we have in section 8.1 is the Gauss-Jordan elimination. And we will also be covering what is Gaussian elimination, which is it was created first, and then Gauss-Jordan is like an extension of that method. So right here, if we take the first part A, it says here, write the system as a matrix equation. So we could say that matrix A will equal to the coefficients of the x sub 1, x sub 2, x sub 3. So we have 1, negative 2, 1. Then we have 0, 1, 2. And we have 2, 3, negative 2. Then matrix X is the one that contains the unknown variables. So that will be x sub 1, x sub 2, and x sub 3. And here we have the constants, which are negative 4, 4, and 2. So to do the Gauss-Jordan elimination, what we do is we construct something that looks like this. So it will be 1, negative 2, 1, 0, 1, 2, 2, 3, negative 2. And then we have that line in the middle that it's kind of like the equal sign. And then we have the matrix B, which are the constants. So I'm going to write that here. Negative 4, 4, and 2. And so that is another way to solve the system. And what we do with that is that our goal is to use the row operations that we have been discussing since I think section 7.3. That is, if you don't remember, you could look at that example. Row operations. And our goal is to transform it into something that on the left side, it will have the identity matrix. And then here we will have some numbers that will be different than the numbers we have here. But those numbers will be the solutions for x sub 1, x sub 2, and x sub 3, which are the unknown variables. Now, it's important that when you construct your, we call this augmented matrix. It has the coefficients, but it also has the constant term, so it has that extra column. So it's important that when you construct your augmented matrix, your system of equations, it's in the same order. So for example, we have x sub 1, x sub 2, x sub 3. The second equation does not have an x sub 1, so it's assumed to be 0 times x sub 1, and that's what you can see here. Then we have x sub 2, x sub 3, so that's why we see the coefficients 1 and 2 here. And then you can see the third equation has every single variable. So yeah, it's important to keep zeros there. And this is the same thing that I was showing you. So after performing the row operations, which we will cover in section 8.1, we end up with identity, and these are the solutions to x sub 1. So x sub 1 is negative 1, x sub 2 is equal to 2, and x sub 3 is equal to 1. And what I was saying is that we have to keep them in order so that we always have column 1 is x sub 1, column 2 is x sub 2, and then x sub 3 is the column 3, so that when we get our answers, they're also in order: x sub 1, x sub 2, and x sub 3. And so that is how it is done. So this is the end of the video. Thank you for watching.